Let D be this solid region within a sphere of radius 5, centered at the origin, and above the plane z equals 4. Now we're being asked here to use cylindrical coordinates to find the volume of this solid. So to begin, I want to start by considering this solid region D in space. So let's think about the bounding surfaces here. We know that this solid region is within a sphere of radius 5. So we've got our beautiful sphere centered at the origin. So we know that this is defined as x squared plus y squared plus z squared is equal to 5 squared, or 25. Now, this solid region is also bounded by the plane. And we have this plane defined at z is equal to 4. So let's take a moment and think about this graphically. So I'm going to start simply by thinking about a two-dimensional interpretation of these three-dimensional surfaces. So we have a sphere centered at the origin with a radius of 5. But this sphere is being cut off by the plane at z is equal to 4. So looking at our two-dimensional interpretation of this three-dimensional region, we can see the bounded solid region. So let's now take this two-dimensional interpretation and think about it three-dimensionally. Voila! So we can see that the upper bound is the sphere, x squared plus y squared plus z squared equals 25, and the lower bounding surface is the plane, where z is equal to 4. Now, because we're using cylindrical coordinates, we need to rewrite our upper bound in terms of z. So we are taking our sphere and solving for z. So I've got z squared is equal to 25 minus x squared minus y squared. And taking the square root of both sides, we are left with z is equal to plus or minus the square root of 25 minus x squared minus y squared. Now, we're only considering the portion of the sphere above the xy plane. So this indicates to us that we only need to consider the positive square root. So z is equal to the square root of 25 minus x squared minus y squared. Beautiful. So now that we have rewritten the upper bounding surface in terms of z, we're ready to state the z bounds. So we can see here that z is greater than or equal to the plane. So z is greater than or equal to 4, less than or equal to the sphere, which is the square root of 25 minus x squared plus y squared. Now, again, keeping in mind that we need to, or that we're required to use cylindrical coordinates in this example, we want to replace x squared and y squared with r squared. So we can say z is greater than or equal to 4, less than or equal to the square root of 25 minus r squared. Beautiful. So we have officially determined the z bounds. Now, all that's remaining in this setup is to find the r and theta bounds. So to find the r and theta bounds, we need to consider the solid's projection onto the xy plane. So if we look at our three-dimensional sketch above, we can see that the projection of this solid onto the xy plane is going to have the shape of a complete circle. But what equation defines this circle? How are we going to find this circle? Well, in order to find the equation that defines this projection in the xy plane, we need to equate our surfaces. So here we go, setting z equals z. We have 4 is equal to the square root of 25 minus x squared minus y squared. And to remove the square root, we take the square, or we square both sides, leaving us with 16 is equal to 25 minus x squared minus y squared. And now rewriting this as an equation that we recognize, we can bring both x and y to the left-hand side. So we have x squared plus y squared is equal to 25 minus 16. And here we go. We are left with the equation of a circle. X squared plus y squared is equal to 9. So we can see that the solid's projection onto the xy plane is a full circle centered at the origin with a radius of 3. So let's think about this graphically. So in the xy plane, the projection of the solid is a circle, a complete circle that has a radius of 3. So looking at this region in the xy plane, we can see the r and theta bounds. We can see that the very smallest radius that the circle could have is a single point at the origin where the radius is 0. And the largest radius that this circle can have is 3. So r is greater than or equal to 0, less than or equal to 3. And then thinking about our theta bounds, so the x-axis represents the ray where theta is equal to 0. And then rotating in a counterclockwise direction around the circle, we're back where we started, where theta is 2 pi. So a complete circle lets us know that theta is greater than or equal to 0, less than or equal to 2 pi. And we have everything that we need. Woohoo! And we're ready now to set up the volume integral. So we know that the volume of this solid region D in space is defined by a triple integral over that region D with an integrand of 1 and our volume differential dV. So for the bounds we just found, we know that the outermost integral is with respect to theta, so that's the integral from 0 to 2 pi. The middle integral is with respect to the radius from 0 to 3, and our innermost integral is with respect to z. So this is the integral from 4 to the square root of 25 minus r squared. And now our volume differential in cylindrical coordinates is r dz dr d theta. So we are now officially ready to begin evaluating. So looking at this triple integral, we can identify the innermost integral with respect to z, and we're now ready to evaluate that inner integral. So we have the integral from 4 to the square root of 25 minus r squared, r dz. So r is a constant here, so this is a general antiderivative, leaving us with r times z. And we're ready now to evaluate from 4 to the square root of 25 minus r squared. So this leaves us with r multiplied by the square root of 25 minus r squared minus 4. So we can now take this and substitute it back into that triple integral above to evaluate the middle integral. So our middle integral is with respect to r. So we have the integral from 0 to 3 of r multiplied by the square root of 25 minus r squared minus 4 dr. So looking at this integrand, we realize that we're going to need to apply a u substitution. So I'm going to go ahead and let u be the radicand. So this is 25 minus r squared. And differentiating with respect to r, we have du dr is equal to minus 2r. And solving for that differential dr, we are left with minus du divided by 2r is equal to dr. Beautiful. So we've got our substitution and our differential. Now we want to be careful here that we change the bounds, because the bounds that we are given belong to the radius, but we want bounds belonging to the variable u. So using u as our function, we have u of 0 is equal to 25 minus 0 squared is 0, which leaves us with 25. And then we have u of 3. So we have 25 minus 3 squared is 9, leaving us with 16. So this is letting us know that our u-bounds are from 25 to 16, which we recognize is a contradiction. Our interval should always read from smallest to the largest numbers. But have no fear, we'll be able to quickly fix this with the order of integration property. So plugging all this in, we can now rewrite our integral as the integral from 25 to 16 of r multiplied by the square root of u minus 4 multiplied by the new differential minus du divided by 2r. And we're excited. We see that these r's cancel each other out. I'm going to factor this negative 1/2 to the front. So we have minus 1/2 multiplied by the integral from 25 to 16 of the square root of u minus 4 du. And now applying the order of integration property, we multiply this integral by a negative. So this becomes plus 1/2 times the integral from 16 to 25 of u to the 1/2 minus 4 du. And we are officially ready to integrate. So integrating by the power rule, we have 1/2 multiplied by 2/3 times u to the 3/2 minus 4 times u. And it is now safe to evaluate from 16 to 25. And we'll give ourselves just a little bit more room here. Now what I'm going to do is think about u to the 3/2 as being the square root of u cubed. This will help to make our evaluation just a little bit easier. So here we go. We have 1/2 multiplied by, so substituting 25 in, we have 2/3 times the square root of 25 cubed minus 4 times 25 minus, now we're plugging 16 in, we have 2/3 multiplied by the square root of 16 cubed minus 4 times 16. And so we can see here that we have the square root of 25, which is going to leave us with simply 5 cubed. And then we have the square root of 16, which is going to leave us with 4 cubed. Beautiful. So we can rewrite this as 1/2 multiplied by 2/3 times 5 cubed, which is 125, minus 4 times 25, which leaves us with 100. And then this is still minus, we have 2/3 multiplied by 4 cubed, which is 64, minus 4 times 16, which is 64. Beautiful. So let's simplify this a little bit. We've got 1/2 multiplied by 2 times 120 leaves us with 250 over 3 minus 100. And now we can distribute this negative through to both terms, which is going to leave us with minus 128 all over 3 plus 64. So we've got a lot of like terms here. We've got the terms that are divided by 3, and then we have our two whole numbers here, or integer values, excuse me. So grouping these together, we have this is equal to 1/2 multiplied by 250 minus 128, which leaves us with 122 over 3. And then we have minus 100 plus 64, which leaves us with minus 36. Now, getting a common denominator within those parentheses, we have 1/2 multiplied by 122 minus 3 times 36 leaves us with 108, all divided by 3. And so we have 1/2 multiplied by 122 minus 108 is 14 thirds. And we can simplify one final time. We know that 2 goes into 14 7 times. Beautiful. So we are left here with 7 thirds. And now we can take this 7 thirds, plug it back into the integral above to evaluate the outer integral. So our outer integral is with respect to theta. So that's from 0 to 2 pi of 7 thirds d theta. Another cute general antiderivative. This integrates to 7 thirds times theta from 0 to 2 pi. So evaluating, we have 7 thirds multiplied by 2 pi minus 0. And this leaves us with a beautiful final answer. This volume of this solid region D is equal to 14 thirds pi. And because this is a volume, we want to be sure to include cubic units. And so there you have it. This is our beautiful final answer.